they do x, y, z functions of any code sample space, however complicated it is, as long as they take values between -1 and +1, this inequality has to be satisfied. Okay? But that is not the case for some quantum random variables. So how do you get the quantum random variables not satisfying this? I just give you the sketch. It's there fully in the book, in this book. So
this is the so-called EPR paradox.
it is also complete. EPR paradox also complete. So there are you have observables taking values in -1 and +1, so-called spin observables. So -1 or +1, and you have the same kind of thing. Okay. So example. This is a generic kind of examples. Some standard notation. Sigma, so 2 by 2 matrices. Sigma 0 is this. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I 0. Sigma 3. This is of course identity. So these three are called Pauli spin matrices. So their eigenvalues are plus or minus 1. So that's this spin means that the values are plus 1 or minus 1. Another way of saying is that they are self-adjoint as well as unitary. Okay? So the spectrum is on the circle as well as on the real line. So it is plus 1 or minus 1. So they are always of the kind 2 times I minus q for some projection. There is another way of saying that. So these are spin matrices, and these 4 things together give you a basis for the 2 by 2 self-adjoint matrices. So all 2 by 2 self-adjoint matrices are just real linear combinations of this. Okay, so they are giving you a basis. That's why it's important. So that is another interesting thing. If you take n cross n self-adjoint matrices as a real vector space, because it's not a complex vector space, right? You cannot multiply with a complex number, then it may not be self-adjoint. So as a real vector space means it has dimension n square. So it's something for compute and see. Okay, so here what we do is we take x1, x2, x3. Together R3, and you get x1 times sigma 1 plus x2 times sigma 2 plus x3 times sigma 3. So you call this as sigma of x. Okay, so that gives you a whole family of self-adjoint matrices. So observables. And one can compute the covariance. Just direct computation. And what you can see then is that if I take any matrix C of this kind, which is positive, and alpha, beta, gamma, you can realize it using three vectors, three unit vectors in R3, X, Y, Z. You can choose so that their inner products are alpha, beta, and gamma. Okay? So you can choose. So any such matrix can be the covariance matrix for three operators, observables of this kind: sigma x, sigma y, sigma z. Okay? I can do that. Okay? So arbitrary. Whereas that one is giving some constraints. Okay? As to they are, all of them actually will be of mean 0 and taking values in plus norm x and minus norm x. Okay? Here it will be spin. If you are taking x, y, z like this, so something you get x, y, z, so that x comma x is 1. They are unit vectors. And this is x inner product y. Beta is x inner product z, and gamma is y inner product. Such matrices you can get. Okay, you can get three vectors to realize any positive definite matrix. Okay, let's say what we call gram matrix. And again, it's a little bit of computation to see that there do exist 3 by 3 positive definite matrices with alpha, beta, gamma violating this. Okay? So you take this as alpha, beta, and gamma. Okay? Violating this. So so anyway, if you want further details, it has been worked out fully in this book. Okay? As to precisely the matrices which violate this. So in other words, there are observables violating Bell's inequality. The spin observables taking values minus 1 plus 1, which violate Bell's inequality. Okay. So now I want to just few minutes. Another thing I want to mention, and then we go to the actual things we want to do, that is orthogonal polynomials and all that. That will be next time. But another general theory, something good to know, is known as dynamics. So in all this, what we are having is a single random variable. It's sort of static. What one is interested in always is a process. So which describes dynamics. So one kind of things what one has in the physical setup is like this. So you have an observable x. Okay. So then after time t, it becomes xt, which is ut x ut star, where ut's are unitaries. So it sort of gets permuted now. X changes to xt, which is utx ut star. So x at 0 is the x itself. Okay. So these ut's you have the structure. U0 is identity. U at s plus t is us times ut. Okay. What we call semi-group. So that is after time s. So x after time s, it becomes us x us star. Another time lapse of time t, then it would be ut acting on this. So that should be us plus t x us plus t star, right? So that is the idea. So if it is after time s, it moves to this us x us star. So any x will go here. After another t amount of time, it will be ut times this times ut star. which is us plus t x us plus t. So then you also assume some continuity. So 3 going to ut, continuous in strong operator topology. So if you assume that, then there is a theorem due to Stone, which is called Stone's theorem.
So the parameter space is the positive real line or the whole?
You can start with the positive one. It would extend to, once you have unitary, it would extend to the negative side also. And also continuity is, you can relax, actually you can have measurability and then you get continuity and things like that. Anyway, so
Semi-group and measurability implies multi-group disability.
very often there are certain cases, certain special cases where there can be some jumps. The jump at 0 is a problem sometimes. There is a possibility of some jump at 0. But for the positive side, usually there is no problem. So then this becomes ut equal to e to the power ith. Okay, the Stone's theorem tells you that this ut has to have this kind of form where h is self-adjoint. So only catch is that in infinite dimensions this h can be unbounded. Okay. But so how do you get hold of this h? So h is basically the derivative of ut. Not h, maybe ih is the derivative.
So what you wrote here, H
Is unbounded.
H can be unbounded.
can be unbounded.
Okay. So this is what happens. If you are restricting ourselves to finite dimensions, then no problem. H will be unbounded automatically. So this is like this. So that means xt is as the form e to the power ith, x to the power minus ith. Called Heisenberg dynamics. Some people also differentiate and write that, like dxt by dt. You see that it is I times h comma x. So then you have to be variable domain and things like that. Bounded case, no problem. So this is called the Heisenberg dynamics. So now what is the meaning? The observable x after time t changes to xt. So if I want to see the moment, okay, so after time t,
It's just a notation for this thing, dx. When you're writing this is notation.
just differentiate it, dxt by dt,
Okay.
and then you see that it ih will come out
That's exactly
and
what you'll do.
I times h comma xt.
It's a comment.
Yeah, it's a commutator because you fix this and differentiate that side and add in some
Yeah,
vector
you
and
do that.
Yeah. So trace rho xt. Okay. So this will be the expectation after time t, right? Because initially it was x, trace rho x was the expectation. After time t, the expectation will be trace rho xt. So I can call it rho at t. Not this. No. This is not. So this is the expectation after time t, okay? Which is trace rho e to the power ith x e to the power minus ith. Okay. Now rho when you have trace, you can commute the things, right? You can bring this here. So this is same as same as this. So in other words, it's trace rho t times x, where rho t is e to the power minus ith, rho e to the power ith. Okay. So you see the expectation has changed. Earlier it was trace rho x. Now it becomes trace rho t of x. After time t, the expectation is trace rho t x. Now this rho t e to the power minus ith, rho e to the power ith. See, these are all unitaries. No? This is ut star rho ut. So this is an automorphism. So this is also a state. Okay, the states will go to states. So rho t is also a state. Okay, so
It's the dynamics of states.
it's a dynamics on states. So instead of saying that x has changed to xt, I can say that x has remained fixed, but the state has changed from rho to rho t. Okay? So it is a sort of dual picture. When you have two things, you can say this is moving with respect to this, or you can say this is fixed, this is moving. Both are equivalent. So this is called Schrodinger picture. Schrodinger dynamics or Schrodinger picture. So this is a dynamics on states, whereas that is a dynamics on observables. But the two are equivalent. So when they initially found the things, they did it separately and got the same answers. And then it was figured out that no, they are actually duals of the same thing. Mathematically, they are equivalent. Okay. Whether you do that or this doesn't matter. I think there is a lot of contribution of Feynman also. And understanding this. So you can also write the differential equation for rho t, the same thing. It will, because rho t is e to the power minus ith, rho e to the power ith, so d rho t by dt. So it will be just with the minus sign. So
This is called the Heisenberg dynamics, and this is the Schrodinger.
this is Schrodinger dynamics.
Previous
Other one is the Heisenberg dynamics. But yeah.
The expectation always remains the same, no?
The expectation is here it is trace rho xt or trace rho tx. It is changing.
No, but
It is changing.
No, e to the power ith and minus ith inside this trace they can just cancel, right?
No, they don't cancel.
Trace of ABCD is not equal to trace of BCDA.
They don't
Only the
cancel.
last.
Yeah.
Only trace of
Only
AB equal to trace of
AB
B.
is equal to B.
They don't cancel. It is changing. Okay? Yeah, it is changing. Okay? And so this is called Schrodinger dynamics, and this is the equation. And you may also do it with the starting with the pure state. So when you just do with this, in that case, rho t is just e to the power minus I. Is ut star u. So this is just e to the power minus ith. Okay. So if you start with the pure state, the rho t also would remain as a pure state. Okay. So you may then write down the equation for ut itself, ut being e to the power minus ith. The same kind of equation you get, dut by dt is minus ih. This is called Schrodinger equation. So this is at the level of just the pure states. If you start with a pure state, it will remain as a pure state. So this is the so-called reversible dynamics. And yeah, the two pictures are equivalent. So this H is known as the energy operator or Hamilton.
So this is a series in H. Converge.
Well, if it's a bounded operator H, then there is no problem at all.
Yeah.
It will converge, right? And you will get a unitary. If it's unbounded self-adjoint operator, then you have to make sense of in what way we are defining this exponential.
Okay.
But there is a whole theory of semi-groups of operators, or even simpler. H is self-adjoint, you have the spectral theory. You can define e to the power, the function e to the power ith. And
And there also it's like there is
It is the same.
It's the same.
It's the same.
Is it possible for any normal number? No, only self-adjoint.
No, the self-adjoint case you get e to the power I th as unitary. The normal case also you may define the exponential. You may get a semigo, but you will not get unitary. Yeah. Here you are getting automorphism. Okay, so I can stop.
So this function is basically taking the line to a circle.
Yeah, it is.